There are places in the universe where time itself seems to shatter, and the laws of physics are stretched to their breaking point. These aren't just empty spaces, but objects of truly impossible density. Can you imagine something so massive that a single teaspoon of it would outweigh a mountain? These are cosmic monsters, and once you cross their path, every single road leads to the end. Picture a star, hundreds of times bigger than our sun, blazing with an unimaginable fire. For millions of years, it's a powerhouse in the cosmos, forging the elements that make up planets, and even us. But this giant is running low on fuel. The colossal outward push from nuclear fusion, which has supported it for eons, is starting to flicker and fail. And then, in an instant, the fight is over. Gravity, always patient, always relentless, wins the war. The star's core collapses under its own staggering weight, triggering the most violent event we know of, a supernova. The outer layers of the star are blasted into space in a brilliant explosion that can briefly outshine an entire galaxy. But what's left behind, the crushed heart of the star, keeps falling inward. If this remnant is massive enough, nothing in the universe can stop the collapse. Not atomic forces. Not nuclear pressure. Nothing. The core keeps collapsing until it crushes down into a point of zero volume and infinite density, a singularity. And around this impossible point, a new kind of object is born, a stellar mass black hole. It's an object so dense that it fundamentally warps the fabric of spacetime around it. Think of spacetime like a stretched-out rubber sheet. A planet creates a little dimple, and a star makes a deeper one. But a black hole isn't a dimple, it's a bottomless pit that nothing can climb out of. The edge of this pit is called the event horizon. It's not a hard surface you could touch, but a boundary, a point of no return. Crossing it is like going over a cosmic waterfall. The very current of spacetime is flowing into the singularity faster than the speed of light. And since nothing can travel faster than light, there's no way out. So, what would happen if you actually took that trip? Well, for your friends watching from a safe distance, it would be weird. As you got closer to the event horizon, the intense gravity would make time for you appear to slow down. They would see you seem to freeze right at the edge, your image slowly fading over what, for them, would feel like an eternity as the light from you gets stretched into nothingness. For you, though, time would feel completely normal as you slipped past the point of no return. Your fate, however, would be anything but normal. You'd experience a process with a terrifyingly playful name, spaghettification. The black hole's gravity would pull on your feet so much harder than your head that you'd be stretched into a long, thin stream of atoms. With a smaller, stellar mass black hole, this grisly stretching would happen before you even reach the event horizon. But these stellar graveyards are just one type. At the heart of almost every large galaxy, including our own Milky Way, there's a supermassive black hole, weighing millions or even billions of times more than our sun. A major puzzle in astronomy is how they got so enormous, so early in the universe's history. Some theories propose they formed from the direct collapse of gigantic clouds of gas, while others suggest they started as smaller, seed black holes that merged and grew over billions of years. These giants aren't just sitting there either, they're active architects of the cosmos. As they feast on nearby stars and gas, the incredible energy they release can shape how entire galaxies form and evolve. And yet, for all their power and complexity, they are beautifully simple objects. A rule known as the no-hair theorem says that a stable black hole can be described by just three things: its mass, its spin, and its electric charge. For decades, scientists thought that anything falling into a black hole was gone for good, its information completely erased from the universe. This created a huge problem, a clash between Einstein's theory of relativity and the fundamental laws of quantum mechanics. It became known as the information paradox. But the story didn't end there. Stephen Hawking made a groundbreaking discovery: black holes aren't completely black. They slowly leak a trickle of particles, now called Hawking radiation, and over unimaginable stretches of time, they can actually evaporate completely. And very recent breakthroughs suggest that information might not be destroyed after all. It seems it gets out, scrambled and encoded in this faint radiation. The paradox that stumped physicists for nearly 50 years is getting closer to a solution, hinting that the universe has a clever way of preserving every last bit of itself. From the explosive death of a single star to the silent giants that steer the fate of galaxies, black holes truly represent the ultimate frontier of our understanding. They are the universe's darkest secrets, pushing us to question everything we think we know about reality, space, and time itself. They aren't just cosmic endings, They might just be hidden gateways to a whole new understanding of physics we've yet to even imagine. What cosmic mystery do you want us to explore next? Let us know in the comments. And don't forget to like and subscribe for more journeys into the universe's darkest secrets.